Good morning, greetings everyone. This is Puya. I'm just going to do a quick review of some of the concepts that you'll see in midterm 2 and solve some of the practice questions I gave you earlier. So the first concept is an open loop comparator, which is just an op-amp circuit with a positive power supply and negative power supply, no feedback at all. Because there's no negative feedback, the op-amp cannot maintain these two input voltages to be the same. So the output voltage, it's going to be equal to positive power supply if V1 is bigger than V2, and if V1 is smaller than V2, V out, it's going to be equal to VCC minus, as you see here. As mentioned earlier, one of the problems with this circuit, with this comparator, is that it's very sensitive to noise and it doesn't have any tolerance. So if V1 gets slightly bigger than V2 or slightly smaller than V2, V out changes. In practice, we would like to have some tolerance and threshold towards noise. So the solution to that is inverting Schmitt trigger or non-inverting Schmitt trigger. So a Schmitt trigger is an op-amp based circuit that takes only one input and it has positive feedback. So because we have a positive feedback, it means that the op-amp, it's gonna work in the saturation mode again. So it means that output, it's either gonna be VCC plus or VCC minus. If our input voltage is connected to inverting pin of the op-amp, this topology is called inverting Schmitt trigger, and this is what you see here. First analyzing a simple case where the negative power supply and positive power supply have the same absolute value. As you remember, op-amp has a very huge input resistance, and because of that, the input current that goes inside the op-amp, it's very negligible, so we can assume it's zero. Because of that, in the positive feedback loop, we have only a voltage divider, so you can just easily calculate the VP voltage, which is the voltage of the non-inverting pin, according to this equation, which is the voltage divider equation. And if VP is bigger than VN, output voltage is going to be equal to the positive power supply, and if VP is smaller than VN, output voltage, it's going to be negative power supply. So I'm just replacing the VP with the voltage divider equation. So as you can see, if R2 divided by R1 plus R2 times V out is bigger than input voltage, output is going to be VCC, and otherwise output, it's going to become negative VCC. And you see that output actually depends on the previous value of the output. So if Vin is a very big negative number, so it means like it's a very it's basically like it's gonna be if Vin is like a very huge negative number, then the output voltage, it's gonna be equal to VCC because VP is gonna be bigger than Vin, right? So as Vin increases, just like follow the green line, as Vin increases, we get to a point that Vin actually becomes equal to VCC, as VCC times R2 divided by R1 plus R2. As Vin gets bigger than this value, at this point, V out, it's gonna switch to negative VCC. So you see that if we start increasing V in from negative infinity to positive infinity, that's the line that we follow. At output voltage, it's gonna switch to negative VCC at this voltage, which is R2 divided by R1 plus R2 times VCC. On the other hand, if V in is a very big positive number, so like somewhere here, because it's a big positive number and it's connected to the inverting pin of the op-amp, VP it's going to be bigger than V in, right? So the output, it's going to be V in is going to be bigger than VP, so output it's going to be negative VCC, right? So VP, it's going to be equal to negative VCC times R2 divided by R1 plus R2, right? If we start decreasing V in, we get to a point that again VP gets bigger than V in, which means that V in it's going to be smaller than negative R2 divided by R1 plus R2 times VCC. So in that case, because this voltage gets bigger than V in, output it's going to switch to positive VCC. So as we decrease the input voltage from positive infinity to negative infinity, this is the line that the output voltage it's going to follow. There is a switch at this point, which is a negative number. This is called hysteresis loop, right? And in this case, because positive power supply and negative power supply have the same absolute value, we have symmetry here, right? So these two values are also the same. So if that's the case, if your positive and negative power supply have the same absolute value, and if you are asked to design a circuit that has this much tolerance, for example 0.01 volt or negative 0.01 volt, it means that for any change that's like happening here within the range between negative 0.01 up to positive 0.01, the output is not gonna change, right? So we can see that like here, like output is not changing, and here output is not changing. So this is like how much tolerance we have towards input change, right? And the same story applies for non-inverting Schmitt trigger. For the non-inverting Schmitt trigger, again we have a positive feedback, which is going to be a voltage divider somehow. Not exactly though, like because here like we don't have ground anymore, but we have like a loop with two resistors, and this time the non-inverting pin of the op-amp is connected to ground. Again, like analyzing the symmetrical case where positive and negative power supply have the same absolute value. Jerry pointed out that I made a mistake when I wrote the equation for non-inverting Schmitt trigger. So I just want to emphasize that if I wrote something other than what you see here on the board, that was wrong. This is the correct equation for the output voltage of the non-inverting Schmitt trigger. So how do we find this equation? If you just write KCL at this point, let's just call this point VP, because there's no input current going towards the op-amp, so you can just assume that the current that goes through R2 is going to be exactly the same current that goes through R1. So V in minus VP divided by R2, it's going to be the same as VP minus V out divided by R1. If you just simplify this through some manipulation, you can find the term for VP. And again, because we only have positive power supply, if VP is bigger than the ground, if VP is bigger than 0, V out it's going to be equal to VCC. And if VP is smaller than 0, V out it's going to be equal to negative VCC. If I replace the value of VP based on the equation that we find, we can reach to this formula here. So again, if this is not what I wrote on the board, please ignore that and just like make sure that you understand this one. If V in is bigger than this value, negative R2 divided by R1 times V out, V out it's going to be equal to VCC. And if V in is smaller than this, V out it's going to be negative VCC. Right? This is just like based on by replacing VP with the term that we find here, and we just like moved V out term to the other side, and like it can be simplified like this. So again, you can see that the V out depends on the previous value of V out, and as you change V in, V out might switch between VCC and negative VCC if these conditions get satisfied. So this time for the non-inverting Schmitt trigger, if V in is a very small number, means like what I meant, like basically like it's a very huge negative number. In that case, voltage of the inverting pin, which is 0, it's going to be bigger than this huge negative number, and because of that the output it's going to be negative VCC. So when V in is very huge negative number, V out it's going to be negative VCC. All right, as you increase this voltage, you get to a point that V in it's gonna get bigger than this term, which is R2 divided by R1 times VCC. It's actually negative R2 divided by R1 times negative VCC. Negative times negative is going to be positive. So at this point, V out it's going to switch to VCC plus. And in the other hand, if V in is a very huge positive number, output it's going to be VCC. And if we decrease input voltage, you get to a point that actually VP, which is this point, it's going to get smaller than 0. Or on the other hand, V in, that means that like V in, it's going to get smaller than this value, which is negative R2 divided by R1 times VCC. So then you see that the switch happens right here. And again, if you're asked to design a circuit that has this much tolerance towards noise, then you just basically have to choose the values of R1 and R2 based on what you have for VCC to satisfy this much tolerance. This was for the simplified case of having positive and negative power supply having the same absolute value. What's going to happen if they do not have the same absolute value? So we want to look at that case. So let's assume that, for example, one of the examples you have in question 1 of the practice is assuming one of the positive power supplies, the positive power supply is 10 volt and the negative power supply is minus 5 volt. And I'm just like analyzing the inverting Schmitt trigger, but it's gonna be the same for non-inverting Schmitt trigger, the same concept. So let's assume that you are asked to have a positive threshold voltage of 0.01 and a negative voltage threshold voltage of negative 0.01. So these two are the same, but our power supplies do not have the same absolute value. So if I write the equation, we want the output voltage to positive 10 volt. When is this going to happen? When V in is smaller than -5 times R2 divided by R1 plus R2, right? Which is what you see here, right? And we want it to be -5 volt if V in is bigger than 10 volt times R2 divided by R1 plus R2. So, and the question asked us to make this threshold value, both of them, make them equal to 0.01. Now, how's that going to be possible? So it means that like this 10 times R2 divided by R1 plus R2, it's going to be equal to 0.01, and -5 times R2 divided by R1 plus R2 is also going to be -0.1. We have two equations and two unknowns, R1 and R2. But this system of linear equations has no solution, because in one hand, this term has to be equal to 0.01 divided by 10, and based on the second equation, the same term has to be equal to 0.01 divided by 5. That's not possible. Okay, so it's not possible to satisfy this requirement with only two resistors. The reason for that is that when V out is positive, the direction of the current is from V out, then goes to R1, then goes to R2, goes to ground. Because V out is bigger than 0, the current always goes from a higher potential to a lower potential. So the direction of the current is first V out, then R1, R2, and then ground. When V out is negative, on the other hand, 0 is bigger than a negative number, so the direction of the current, it's going to be from ground, then R2, then R1, then V out. Because we basically have exactly the same path from the V out to ground and ground to V out, in the case that our two power supplies do not have the same absolute value, we cannot end up with the same threshold voltage, because this is, as you can see, it's not possible. So as I mentioned here, this is like regarding the direction of the current. So what is the solution here? The solution here is introducing a directional resistor. So we basically want to make these two equations different. How can we do that? By just like adding another resistor here, like let's say in parallel with R1. So in that case, what happens is that when current goes from V out to ground, current goes from V out, then R1 to R2. But when current goes from ground to V out, it goes from R2, then R1 parallel with R3, then V out. So if we do that, then we end up with two different equations. Like one of them is the same as the one we saw before, when current goes from V out to ground, as you can see here. But in this case, this is like the equation for this circuit. So in this case, when current goes from ground to V out, then voltage of this point, it's gonna be -5 divided by R2 divided by R1 in parallel with R3 plus R2, right? Because now we have these two resistors in parallel with each other. right? So now we have two equations and three unknowns. Usually when your number of equations is less than your number of unknowns, it means that you have a degree of freedom. You can end up with many different answers, many different solutions. What does that mean? It means that like you can just like choose any number for one of the resistors and find the value of the other two. So for the case that you don't have symmetrical power supplies, then we can solve this by adding a parallel resistor with a diode in the right direction. So you just like have to make sure you add this diode in the right direction. That depends on the values of the positive power supply and the negative power supply. So for example, if this diode for this case was pointing the other way, it would have actually made the problem even worse. Like you have to make sure to choose the right direction for the for the diode. If, for example, if this was 5 volt and negative 10 volt, then you could have switched the diode in the other way. You actually should have. So I'm just repeating that part here. This is actually not a comparator because it takes only one input, and it just tells us like how much it is bigger than 0, like based on these values. Like if it basically like it makes a decision for V out based on like how much this is bigger than 0 or smaller than 0, depending on the values of our threshold, which is dependent on the values of the resistances. So what if we want to compare two different voltages as we did in the open loop comparator here? So in that case, we can use a circuit that we've seen before called subtractor. This is a subtractor. I derived the equation for subtractor one more time. If you forgot like how this is done, this is like showing how you can find the value, the relationship that relates the output voltage to input voltages. And you can see that that depends on all the 4 resistances that we have in the circuit. If we choose all the resistors to have the same value, then this can simplify to this equation, which shows that V out is equal to V1 minus V2. I'm sorry, my cat wants to also learn, but not today. So if we choose all the resistors to be the same, V out is going to be equal to V1 minus V2. So if we want to compare two different voltages, two different signals, and see like if one of them is bigger than the other one, we want to have like a positive voltage. If V1 is smaller than V2, we want to have a negative voltage. Then we can just like first have a subtractor circuit that provides us with V1 minus V2. How can we achieve that? By having all the same values for all the resistors. And then provide this as an input to the Schmitt trigger. So in this case, if V1 minus V2 is smaller than a small voltage, or if V1 minus V2 is bigger than a certain voltage, then our output, it's going to switch between VCC plus and VCC minus. So this was actually the answer for all the parts in question 1. If your power supplies are symmetrical, you can use either the inverting Schmitt trigger topology or the non-inverting Schmitt trigger topology. If your if your power supplies are not symmetrical like this case, you have to introduce a directional resistor, either the diode facing towards V out or towards V in. One thing that you have to remember, that if you want to compare two different voltages, first you can add a subtractor circuit which provides you with the difference between V1 minus V2. Now, if you want to know if V1 is bigger than V2, it means that V1 minus V2 is going to be bigger than 0, right? If V1 is less than V2, it means that V1 minus V2 is going to be less than 0. If V1 is smaller than V2, right? But we don't want this to be exactly 0, otherwise we would have the same problem that we had with the open loop comparator. So that's the tolerance, that's the threshold that we want to provide using the Schmitt trigger and these resistors. It is possible to have a circuit with only one op-amp that does that for us, but that's beyond the scope of this course. I'm sorry, I made a mistake in the question 1 asking you to only use one op-amp. It is possible, but that wasn't my intention. That was a mistake. I'm sorry about that. So like something like this would be okay for question 1. The second concept that the second concept that we saw in the class was an oscillator. Why is it called astable? Because like it basically means that the output is not stable. It switches between two different values. And it was an interesting circuit because it doesn't have any input signals, but output signal switches between VCC plus and VCC minus. Basically, these are our power supplies. And because, again, we have a positive feedback, the op-amp operates in the saturation mode. So the output, it's either going to be VCC plus or VCC minus. If this voltage is bigger than this voltage, it's going to be VCC plus, and the other way around, it's going to be VCC minus. Let's just again analyze the simplified case where VCC minus is negative of VCC plus. So I wrote the term again, like if VP, the non-inverting voltage, is bigger than the inverting voltage, V out is going to be VCC. If the non-inverting voltage is smaller than the inverting voltage, V out is going to be negative VCC. Now let's look at the circuit one more time. In the positive feedback, again, we just have a voltage divider because there's no input going towards the inside, like into the op-amp. It's I in of op-amp, it's almost 0. So here VP is basically R2 divided by R1 plus R2 V out. Okay, so it's going to be either positive VCC or negative VCC times this term. Now let's look at the inverting pins voltage. The inverting pins voltage, it's just like an RC circuit, and it's going to be the voltage across the capacitor, right? And we've already seen the formula for like an RC circuit and how the voltage of the capacitor changes. If you remember, this was the general formula for an RC circuit and the capacitor voltage in it. Now, let's again look at this. So we said that V out, it's either going to be VCC positive or VCC negative. If V out is VCC positive and this voltage, it's going to be bigger than ground. So again, the current, it's going to go from R to C. So capacitor is going to start charging. However, if V out is equal to VCC minus, and we assume that VCC minus is a negative number, the current is going to go from ground to V out. So two different directions for the current on this feedback. So capacitor charges when V out is positive, capacitor discharges when V out is negative. So let's just assume that V out starts with a positive voltage, like if this is like already like that's a reasonable assumption. So in that case, if the capacitor voltage is 0, this is going to be bigger than Vn. So like the capacitor starts charging and it tries to reach VCC, right? It basically, this is initial voltage of the capacitor, and this is the final voltage that it wants to reach. But before it reaches this ultimate goal, it gets to a point that the voltage of the capacitor gets bigger than the voltage of the non-inverting pin. And once this happens, once this voltage gets slightly bigger than this voltage, and the op-amp is in the saturation mode, so V out, it's going to jump to VCC minus. This is what's happening here. So a capacitor charged here. Now, the capacitor has an initial voltage which is equal to this value, right? And it wants to reach negative VCC because V out is negative VCC. So in this case, this is going to be VI, this is going to be VF. So capacitor starts discharging, but again, the same thing happens. So the capacitor voltage starts decreasing up to a point that it gets smaller than VP. So VP gets bigger than VN. And output voltage again at this point jumps back to positive VCC. So the capacitor starts charging again. So and this story continues. Sorry, I made a mistake here. This story continues. In the case that we have symmetrical power supplies, it means that their absolute value is the same. If that's the case, doesn't matter what R and C are, doesn't matter what R1 and R2 are, we always end up with a duty cycle of 50%. Why is that? Because the time constant of charging, it's exactly the same as the time constant of discharging. Both of them are equal to RC. Doesn't matter where the direction of the current is. Is it going from V out to ground or from ground to V out? Right? And if you can't believe this, you can actually write the equation and find the time T1 and T2, which is what I did here. So when charging, this is the equation. VC, it's going to change like this. I wanted to find the value of VC at T equal to T1. Right? And I know what the value of VC at T equal to T1 is. Right? So I have it here. Once I make that equal, then I can find the value of T1. If I write the same thing for T2, I have VI, I have VF, I know the value of VC at T equal to T2. If I write the same equation for finding T2, if you look at these two equations, they're exactly the same, just like one is multiplied by -1, which is okay, we can cancel it out. It means that this equation would give the same value for T1 and T2. So we would end up with a duty cycle of 50%. Okay. One thing I forgot to mention is that we assume that our circuit is in the steady state. It means that we ignore the first charging time, because here, like, it basically our capacitor starts with a 0 voltage, right? But from the next pulses, they always start from the negative voltage, right? So like we assume that we're already in the steady state, so ignore this one. That's why I calculated T1 here and T2 here. I didn't calculate this one because that wouldn't be full T1. But this is the same as this T1. This is the same as the next one, and so on. Okay, so if you want to have a duty cycle of 50%, you basically want to, if you want to generate an output that oscillates between two symmetrical negative and positive power voltages, then this would always satisfy the equation. Doesn't matter what the values of R and C is, like you end up with like 50%. Of course, like if you change the R2 and R1 and R2, this basically can like make this like faster or smaller, like so. But in terms of the duty cycle, this is not going to be impacted by the values of R1, R2, even R or C. And for this case, if you find T1, you can find it like this. If you also, like we saw that T1 and T2 are the same, so the same value here. You can see here T1, the value of T1 and T2 depend on 4 different parameters: R, C, R2, and R1. Okay, so by changing this, you can make this signal go faster or slower. So we can change the frequency of the signal. Its duty cycle is always going to be 50% because T1 and T2 are the same. But you can change the frequency of it or the period of the signal. Okay, so you can change the period of the signal. Again, let's say like for one of the questions that we had, I think it was question 2, it was asking you to design a circuit that has T1 and T2 both equal to 20 microseconds. So you just make this one equal to 20 microseconds. You have one equation with 4 unknowns. So you have 3 degrees of freedom. That means you basically can choose the value of 3 of these parameters and find the value of the other one, right? And because of that, one way to solve this is basically making all these resistors the same. If we do that, if we make R1 and R2 the same and equal to R, it means like we're using 3 of the same resistors, then this equation gets simplified. This basically just becomes 3, and you can find like what's like by choosing any value for R, you can find like what's the capacitor that you need. I just want to repeat that this is only one way of solving this design problem. Design is an art, right? So where does the art part come from is basically comes here, because now you have so many choices. There's not just one answer. My answer can be different from yours, and both of them can actually give us the same T1, right? Because we have 3 degrees of freedom. Like we have only one equation for 4 different unknowns. There are infinite answers for this equation. You can choose like R to be 1, C to be 1 microfarad, R2 to be 100, find the value of R1, right? You can choose like C to be 2 microfarad, R2 equal to 1, R1 equal to 100, find the value of R. So there are many different answers. One simplifying like common answer is to make R2 and R1 the same. So that way like this reduces to 3. And you can find the value of C from that. It's not necessary though, right? So if you tell me that like you want to have R2 to be equal to 2 times R1, that's fine too. Then instead of ln3, you end up with another number here. Another mistake I had in the practice questions, and I'm sorry for that, is that I shouldn't have given you the both T1 and T2 and the frequency. A frequency of the oscillation is always going to be 1 over T1 plus T2. In some parts of those questions, these values, the value that I gave, was not compatible with the value based on T1 and T2. So I just like corrected the question 2, if I can find it. It's right here. So if I see question 2, so for question 1, you can use 2 op-amps. For question 2, just ignore the part that it was asking you to use a frequency of 1 kilohertz. Okay, so that was a solution for the case that we had symmetrical power supplies. VCC minus was equal to negative VCC plus, right? And in this case, always duty cycle is going to be 50%. Always T1 it's going to be equal to T2, and I told you the reason for that, because the actual physical reason for that is because the time constant of charging and discharging are the same. Now, what if we don't want to have T1 equal to T2? So what if we want T1 to be bigger than T2? What if we want T1 to be smaller than T2? So if you want T1 to be bigger than T2, T1 is for charging, T2 is for discharging. If you want T1 to be bigger than T2, it means that you want the time constant of charging to be bigger, right, than time constant of discharging. So what happens if I add another resistance here with a diode? It means that this is like a directional resistance. Only is going to be in the circuit if the current is going from ground to V out, right? So when does this happen? When the capacitor is discharging, right? How about when capacitor is charging? The current only goes from the R resistor to the C. This one is going to get blocked, right? So the time constant of charging is just RC. The time constant of discharging is R in parallel with RP times C, right? And this is always going to be smaller than R and also smaller than RP, right? So in this case, time constant of discharging, it's going to be smaller than time constant of charging. And because of that, T2, it's going to be less than T1. And the same thing happens if you rotate the direction of the diode. This time, the charging, it's going to have a smaller time constant, right? So in this case, you end up with duty cycle, which is going to be less than 50%. If you have both of them, then based on the values of RA and RB, you can make the duty cycle less than 50% or bigger than 50%. Okay, and as mentioned earlier, sorry about that. As mentioned earlier, choosing R1 equal to R2 is only one solution. It's only one option. You can also like make R1 3 times bigger than R2, or like any other, based on the available resistors that you have, or based on the cost, or based on different other design requirements. Okay. So now, in another question, I was asking you to derive the general equation for the case where we don't have symmetry over power supply, where VCC minus is not equal to VCC plus, right? So it means that V out might be like positive 15, or -10, let's say, right? There's no symmetry anymore. So now also like the charging and discharging transition points is not going to be symmetrical. One of them happens at this voltage, which is the voltage divider equation when our voltage is VCC plus, and the other one it's going to be this. So these two do not have the same absolute values. Now here, based on what you have, you end up with, based on like the values of VCC plus or VCC minus, you can end up like with a duty cycle which is less than 50%, bigger than 50%, or equal to 50% if these two become equal. So I ask you to find a general equation for that. Again, you just like need to write the equation for charging and discharging. You have VI and this is VF for charging, and you know what the voltage is at this point. So this is going to give us one equation. This is VI, this is VF, this is VI. Right, this is VI. And for discharging, again, this is going to be VI. This is going to be VF. This is going to be VI. Right, and we know like what the voltage is after T2 seconds or microseconds. So this now gives us two different equations. So in this case, T1 and T2 are not going to be the same because VCC plus and VCC minus do not have the same absolute value. So now you have two equations and four unknowns, right? So if you simplify question 1 and question 2, you end up with two different equations, one for T1, one for T2, right? And again, you have degree of freedom. So based on R1 and R2, you can find T1 and T2. This is like what I asked you in the questions. Another thing I wanted to review for you is the concept of an average of a signal, a periodic signal, or the DC value of it. There are different notations. Some people show it like this with a bar on top, or with angled brackets around, or we also like can call it the DC component of a signal, or some people like show it with F0 because the frequency of DC is 0, right? So what is the mathematical definition for it? It's just 1 over the period and the integral of the function over 1 period, right? So that's basically what the definition is. Let's say like you have a periodic signal, like a pulse signal with a duty cycle dt. What is this term? It's going to be 1 over t, dt times vp. So it's going to be d times vp. Some of you forgot to divide it by t. Like you shouldn't see any time component here for this circuit. What if we have a triangular wave? Now it doesn't matter again, like it doesn't matter like if it's like this or like this or like this, right? If you take the integral, it basically means like you want to calculate the area of the triangle. What's the area? It's always half of base times height. So you can actually see that like all of these triangles have the same DC value. One other part that you had for the finding average was a sine signal that was shifted up a certain amount, VD in this case. So one way of solving this, like if you want to find what the average of this shape is, you can calculate the area under the curve. So that's going to be the integral, 1 over t integral of the function over time. So once this is calculated, you find out that, oh, my average voltage is just VD, right? And once you do this, you also see that always a sinusoidal signal's average over one period is always going to be 0, right? So the only thing that it's going to give us some DC value, it's going to be the DC offset. One other way of like seeing this is basically by seeing that we wanted to first calculate the area of this shape, but you can assume, well, like it definitely this area here, it's going to be equal to this area. So if you replace this area with this area, we end up with just like a rectangle, right? And you know how to calculate the area of a rectangle, and you can find the DC value. That's why this is called DC offset. It basically means that the signal itself doesn't have any DC value, just like it's shifted up, and because of that we end up with a DC value. For this other part that you're asked to calculate the average value, we apply the same concept, the mathematical definition of average, right? Because the function is 0 from t over 2 to t, so the limits of the integral, we can just like make this from 0 to t over 2. If you calculate it, this is the answer you should find. Okay, next thing was a question that I gave you, the current waveform for a capacitor, and I asked you to draw the capacitor's voltage, and also like asked you to find like some kind of relationship between all the given numbers. So as mentioned in the class, there's a concept called amp-second balance. It means that if a system or a circuit is in the steady state and it has capacitors, sorry, this is amp-second, yeah, if it has capacitors, and if it's in the steady state, it means that the area, or if the integral of IC over one period has to be equal to 0. Why is that the case? What's the physical meaning of that? Means that if a capacitor wants to be in the steady state, it means that if it gets charged or discharged within a period, these two values should basically match. If this much current goes out of the capacitor, if you want to end up in the steady state, you're not supposed to add any more energy to it. So you basically have to provide the same amount of charge or energy. If you remember, Q or I is equal to dq over t dt. So Q is equal to integral of I dt. So this area actually represents charge. And amp-second balance tells us that the charge that goes inside a capacitor, it's going to be the charge that gets released from the capacitor if we are in an AC steady state. One other way of explaining this is by just like the energy concept. It means like the same amount of energy that goes inside the capacitor, it's going to go out of it. If we just ignore like the like friction or different things, or like not friction, if you ignore like the non-ideal properties. So by applying the amp-second balance, we end up with this equation. That was like part B of this question. The part A of this question, I just basically wanted you to like get familiar, or like more familiar with the equations that govern the behavior of a capacitor. right? If you have I, you should be able to find V. If you have V, you should be able to find I. So now here we have I, right? From 0 to T1, it is equal to Y1. From T2 to T, it's equal to Y1 as well. From T1 to T2, it's a line that we know two of its points, right? I'm not gonna go over this, but like any line can be written as y equal to ax plus b, which a is the slope, and this is the value of the function at x equal to 0, right? So for this line, if you want to find the equation of the line, it's very straightforward because we know what t1, what y2 is at t1, and like what y3 is at t2. It's going to be a line, and we can find the exact coefficients. And since IC is equal to C dVc over dt, Vc is going to be 1 over C integral of IC dt plus the initial voltage, right? For a line, if you take integral, you end up, sorry, if you have a constant value, if you take integral, you end up with a line. If you have a line, if you take integral of a line, you end up with a second order polynomial, a quadratic polynomial. So that's what we have here. And this one is very similar to question 1. And again, if that's the case, you can actually draw the capacitor's voltage. These values depends on all the parameters that we have. So you can actually change like the behavior slightly. And another thing that is a result of amp second balance is that like the voltage of the capacitor at the beginning of a period is always going to be the same after the end of the period. Okay. And the diode characteristic for a PN diode and like a Zener diode, this is like the practical characteristic, right? Both of them have a forward bias, which is around 0.7 up to 1 volt, sometimes it's even smaller. The regular diode, it's a reverse breakdowns when the voltage that gets applied to it, it's very huge, right? So that's when the PN diode breaks. For the Zener diode, no, that's not the case. Usually the breakdown point, it's a very constant, like, or it's like similar to constant. And you basically, like, you always end up with a constant voltage. Zener diode can work as a constant voltage source. The ideal cases for them, like, we don't have like the forward bias voltage drop, we don't have reverse breakdown, and yeah, so that was it, I guess. For this equation, I just wanted to tell you that these concepts of amp second balance and volt second balance, these concepts are important concepts, and it doesn't only apply to circuits where we just like have capacitors or inductor. If we even have resistors, and if our circuit is in the if I'm gonna repeat that. So it doesn't necessarily like in the class we studied the concept of volt second balance and amp second balance without having any resistors, right? But if we have a circuit that is in the steady state and it has resistors and capacitors, we can still have the volt-second balance or amp-second balance for this case. One thing I forgot to mention for this question, again, that's my mistake, I'm sorry. I forgot to give you the initial voltage. Depending on what the initial voltage is, you might not end up in a steady state mode, right? But for this one, I could write all the equations and I could find like what's the resistance that can give me a steady state response. So how did I do that? What's the concept of volt-second balance? It means that you get charged at the same amount that you get discharged. Now, in this case, again, I use the general formula for the capacitor voltage of an RC circuit. We have, again, similar to the previous question we solved, if the voltage is positive, we have two resistors in the circuit. If voltage of the input becomes 0, the capacitor is going to discharge. We only have the 100 ohm resistor in the circuit. So I wrote the equation for capacitor voltage for the time that VI is equal to 10 volts. So we have VI, VF, VI, and I wrote that, and at t equal to period over 3, I find like what the value of the capacitor voltage is, right? Now, the amp-second balance tells us that now, if we want to end up in the steady state, the capacitor has to discharge exactly to the voltage that we started from, right? So I again wrote the same thing, but this time for the discharging period, right? So I knew what my initial voltage is. I knew like how long I have to wait, and I knew like what voltage I have to end up at. So I did all these calculations and I find the value of RA. The same thing applies to the amps volt-second balance, like if we have an inductor here. Just like when you have an inductor, I just want to make sure that you guys know that. Let's say if this is an inductor, like if you apply like positive 10, then VI should be given, let's say if it's 0 amp, II, 0 amp. IF, final value of the current, is gonna be just like the input voltage divided by R, because at t equal to infinity, the inductor basically works as just like a conductor. And so like for the circuit with the inductor, you can just like use the same formula, just make sure that this is going to be I, and you can find the initial and the final values and solve for RA or RB. In the Sawtooth wave generator, we have two circuits. One is for charging, one is for discharging. When the capacitor charged with a constant current voltage, it's going to increase linearly. When it gets discharged using, again, like a constant current source, you can see that the voltage drops to 0 this way. So when do we have charging? When this circuit is not, when this part of the circuit is not active, right? So when input voltage is equal to 0, capacitor is going to charge. When input voltage becomes, let's say 10 volt or 5 volt, then now this switch is on. You would have this discharging current that goes through the ground through here. This part is done in the in the class, so I'm gonna just like quickly go over it. You can calculate the exact value of the peak voltage using the formula, either using this line or this line, because you know the slope, you know how much time has passed, so you can calculate this. So this is just like a design question for the Sawtooth wave generator. So we did say that V peak is going to be equal to I discharge times dt divided by C, or it can also be equal to I charge divided by C times 1 minus dt, right? So like both of them should give us the same value, right? So in this case, if you want to find like what is the duty cycle, what is the current, then we make everything equal, and this is what we end up with. Again, we only have one equation and two unknowns, so we have a degree of freedom. So most of the time when we say like triangular wave, we want to have something like this, especially in the concept of modulation that you'll see later. We want to make this one as sharp as possible. So it means that we want to make D very high or not very close to 0. So you are also given this extra piece of information that the maximum current that can go through a collector is going to be 1 amp. Now, generally when you want to, as mentioned, generally when you want to generate a Sawtooth wave generator, you want to make dt very small. The duty cycle is small, right? So to make it look like this. But according to this equation, if I make D very small, it means that the discharging current has to be very high. But we have a limit on that. So it means that discharging current is always going to be less than 1 amp, right? So this cannot be less than 1 amp. And based on that, we can find a minimum value for the duty cycle. So our duty cycle, in that case, we can just randomly choose something that's bigger than the minimum we get from this value. So this is the rest of it is very similar to how this question is solved in the lecture notes. So you can find like all the RE, RB values and everything else. Okay. Excuse me again, sorry. One thing that I also wanted to mention here is that our capacitor, our Zener voltage versus current characteristic is this one. When we say that Vz is equal to 4 volt, it means that we are at this point of the operation. Any Zener diode or any equipment should come up with a specific data sheet, right? So like you can find out based on that data sheet what's the rated current of the Zener diode, at what current we would end up with 4 volt, right? Once you find that based on the data sheet, you can design your RX so that it would satisfy the rated Zener current going through here, right? So this is like the part that's done here. It basically writes a KVL here because we can assume that the base current is almost zero. So then based on the rated current that can be calculated, that can be just like looked or found from the specific data sheet, you can find the value of Rx. So in this case, I don't have any data sheet like in hand right now, so like I just write the formula, and that should be enough for you if this is like indexed. And the last question, boost converter. Have inductor L, a switch S, and a diode D, capacitor. So for the sorry, like my battery died, so I had to do this in a new video. So for the boost converter, we have an inductor, a switch, a diode, capacitor, resistor. The boost converter steps up the voltage, basically using an inductor. We save some energy in it, and then that energy gets released into the load, and our output voltage, it's going to be bigger than our input voltage. One thing about the boost converter is that the current that goes through our load, because we have a capacitive filter here, the current, we can assume that it's always VO over R, and by VO, like our VO, it's usually specified like what output voltage you want to have. So if we have that, we can calculate what's the current that goes through here. The output voltage, it's going to be a DC voltage, but it has some ripples. So let's say it's going to be like 40 volts plus minus 2%, something like that. That's why like I'm using the average here. So like it's going to be 40 volt. We did all these in the class. I'm just going to go through it like very quickly. When this switch is on, this diode, it's not going to be in the circuit, so inductor voltage, it's going to be the same as VI. And in the same scenario, the capacitor voltage, it's going to be negative of the resistor. The capacitor's current, it's going to be negative of the resistor current based on the notation, the direction we chose for IC and IR. So, and we said that we assume that IR is always going to be VO over R, so it's like basically a constant negative current. In reality, it's going to be exponential because this is an RC circuit, right? But because we assume that the time constant of this is going to be very big compared to our period, so we can assume that's a reasonable assumption to assume that this is going to be a constant current at this point, which is going to be equal to negative of VO over R. When the switch is off, the diode is not going to be on because inductor has some stored energy. It's going to keep the diode open, and we have an RC circuit at the end. Our inductor voltage, it's going to be VI minus VO, so this is what we have. Because of the volt-second balance, these two areas have to be equal, so this definitely has to be negative. That shows that VO has to be bigger than VI. When you apply constant voltage onto an inductor, its current, it's going to increase linearly with the slope of 1 over L times that voltage. So that's what we have here. And the same thing, it's going to happen for the discharging period. If we are in the steady state, you should end up at the same level, right? That means that this charging and discharging has to be the same. You can actually calculate what is this value once through this line, once through this line. It's going to be 1 over L times VI times dt, or 1 over L times VI minus VO times 1 minus dt. These have to be equal. You can also write the same equation by the volt-second balance, making these two areas equal. And based on that, we found this relationship between output and input voltage. So these two I already explained. We just also said that the resistance current, we assume that it's always constant, equal to V over R. When this diode is not conducting, IC is going to be equal to negative of IR. When the diode conducts, IC is going to be IL minus IR, right? Based on KCL, IC is going to be IL minus IR, right? So it's going to have the same shape as IL, but it's shifted down this much. Okay, so in question 12, I asked you to calculate the value of inductance and the value of capacitance based on the characteristics I gave you for the ripple. So if I ask you what's the inductance, you can calculate the inductance based on this. So first of all, we said 20% of IODC, it means 0 point times 2 times VO over R, that's IODC. So we want our delta IL to be this much, right? And this is what delta IL is, right? So you know delta IL, it's going to be 1 over L times VI times dt. It's based on this line. The slope of it is 1 over L times VI. It goes up and this much time, so that's how you can calculate it. You have VI, you have D, you have T, you can calculate L. To calculate C, this is basically this is how much current is basically discharged from the capacitor, and this is like how much charge gets discharged from the capacitor, how much charge goes into the capacitor. And based on amp second balance, these two areas have to be equal. So this delta Q has to be exactly equal to delta Q, right? Delta Q, we know that it's equal to C times delta V. That's a capacitor's characteristic. At the same time, this delta Q, it's gonna be VO over R times dt. It's gonna be this area because Q, it's integral of I dt, right? Amp second is the unit for charge, right? So if you make these two equal, you have VO, you have R, you have D, you have T, you have delta V, which is given 2% of VO, so it's going to be 0.02 times VO, whatever VO is, 30 volts. So you can calculate what the value of C is. Now, once you increase your resistance, the value of current goes down, right? IO is equal to VO over R. As you increase the resistance, IO goes down, right? And the same for IL, right? And the average of IL is always equal to IR. Okay, so the average is always VO over R, right? At the same time, the average of a triangle is delta IL divided by 2. But before we get to this point, as you increase R, you get to a point that your inductor's current starts from 0, goes up to delta IL, and reaches to 0 at this point. This is called boundary conduction mode. It means that current gets momentarily 0 but it doesn't stay 0. In this case, the average of IL, it's gonna be VO over R, and it's equal to delta IL. Right, so you can actually calculate for what value of R you will have a waveform for IL like this. If you increase R further than this critical value, it basically means that now your inductor that you asked for help, it wouldn't have that much enough energy to make this current flowing through this diode through the whole period. If you increase the R, you're basically making your IO smaller, so you get to a point that your inductor's current reaches 0 before the end of the period, right? It means that your inductor's current is gonna discharge very fast, right, before the end of the period, and the current becomes 0, and this diode would be basically disconnected. It's not going to be conducting anymore. This mode of operation is called DCM. You will see this in your future courses. I just wanted you to know what DCM is, what CCM is. When we say CCM, continuous conduction mode, it means that we always have some current going through our inductor, right? It never reaches 0, right? But in the discontinuous conduction mode, at some time, we don't have any current going through our inductor. Okay. Some other questions that I didn't solve, but I think they're very easy. We did question 1, 2, 3, 4, almost 5. We did that. 6 we did. 7 we did. Okay, so for this one, we also you can figure out which ones are for charging and discharging. Charging and discharging of the capacitor, and what this one was for. For example, this one is for making sure that you work at IZ rated and make your VZ equal to what you want it to be. And the BJTs, one is for charging, one is for discharging, and so on. Question 9 is basically a combination of many different things that we saw earlier. This one is an A-stable oscillator. You have the frequency, you have the duty cycle. You know it's going to oscillate between -10 and 10, right? So because the duty cycle is less than 50%, it means that you have to have an extra resistor with a diode. The ramp generator, we did something similar to that. It's similar to the previous question we did. So we just want to have a ramp generator that goes from 0 to 5 volt. You can calculate that. Okay, and once you generate your ramp, your Sawtooth waveform, you can subtract it from a sine signal using a subtractor. I forgot to give you the frequency of this one. You can make it equal to 300 hertz, but it doesn't matter any value you want to use. Just I wanted you to subtract this so that you end up with a signal like that it's either gonna be just basically based on it's either gonna be positive or negative, and then you provide that to your Schmitt trigger. Sorry, this is not the input of the Schmitt trigger. This is going to be the output of it. So this is either going to be positive or negative, the VDIF, right? And you provide it to the Schmitt trigger, and based on that, you generate a PWM signal. For volt second and amp second balance rules, I already mentioned that. Means that for volt second means that the flux going into an inductor, it's gonna be the average of it over one period, it's gonna be 0. Or at the same time we can say that the energy that goes into an inductor, it's gonna be same as the energy coming out of it if we are in the steady state. The mathematical interpretation is that the integral of voltage over time, it's going to be 0 for one period, or the current of the inductor at the beginning of a period, so I at t equal to 0, it's going to be the same as I at t equal to the end of the period. Exactly the same thing for amp second rules, just like this is for charge, this one was for flux. The energy of the input energy and output energy is going to be the same. The capacitor is going to charge and discharge the same amount if we are going to be in the steady state. The integral of I dt, it's going to be 0, so the net charge it's going to be 0. And also like v at t equals 0, it's going to be equal to what v at t equal to end of the period. This question we did that, we did this part, this is very similar. And question 12, I already did that as well. Thank you so much. Good luck.